This is Dr. Holt. This video is on free body diagrams within the physics curriculum. My purpose is to define what is a free body diagram and to emphasize the importance of drawing them. A free body diagram is just a picture that represents one or more objects along with the forces acting on those objects. The objects are usually drawn as a circle or a small dot, just basically for the sake of simplicity, and the forces are always shown as vectors. Free body diagrams are important because they help us see forces as vectors. And if you can add vectors, you can analyze free body diagrams. Free body diagrams are essential in physics, so don't be dumb. From experience, I've had students that refuse to draw free body diagrams, or they're arrogant and they think they can solve problems without it. It is good to develop good habits in drawing free body diagrams. Example here, this is a picture of a student that's on a test that did not draw a free body diagram. This is a picture of a student who has finished a test who has always drawn good free body diagrams. Students in my class, or students in my classes that have not drawn free body diagrams have done worse on almost every quiz and test. And this has to do with basic first-year physics as well as calculus-based physics. Every successful engineer or physicist draws free body diagrams. In my class, if you ask me for help and you have not drawn a proper free body diagram, I will refuse to help you. Okay, so it's essential. If you have questions, I expect you to have a very neat, properly labeled free body diagram. So what is a free body diagram? Here I have an individual. This individual has mass. It's just standing on some type of ground. And here I would draw the individual. I would represent them with a single dot. They would have two forces coming applied to them. They would have a normal force, and we'll talk about that in another video exactly what a normal force is. But they would have a normal force of the earth pushing back up on the man. They would have a force of gravity of the earth pulling back down on the man. So my free body diagram would look something like this. I like to also label the axes, and something you can do here is you could label this as like an x-axis here, and you could label this as a y-axis here. Often I will just draw these lighter as like a dash, so I don't want that to be interpreted as any type of force. If the forces have the same magnitude, I'd like to put a slash through them to basically state that they are of the same magnitude. Proper ways to label the free body diagrams. With the forces, I usually put some type of identification as the type of a force. This could be a normal force, it could be some type of tensing force, it could be a pushing force, or a pulling force. Now, you kind of have some liberty as far as what you want to call this. If it's a normal force, I like to see it drawn as a normal force, or a tension force as a tension force. If it's a pushing force by hand, you could put a PH or an HP or something like that. So it's some way for you to identify what's causing that force. The second thing I do is identify the force dealer, is what's causing the force. Okay, an object cannot cause a force upon itself. So this one is always going to be what I call the force dealer. It could be the earth, it could be some type of rope, it could be, like I said, a hand, something that's causing the object or causing the force. Here I usually put like an arrow or a slash. I probably often use slashes more than arrows. But if you're a first time person drawing free body diagrams, it might be good to draw an arrow so you know that the dealer is causing the force onto the feeler. Now the feeler is going to be what's feeling the force, okay? So if you're drawing a free body diagram of the man, this is going to be the force. This is going to be the force feeler, or you're going to represent this with the man. This is what's having the forces applied to it. Okay, force pairs. Let's define what force pairs are. Okay, force pairs will always act in the same line of action. They will not go the same direction, but they will be the same line of action, meaning if one goes up, the other one will be going in that same axis. If one goes horizontal, the other one will be going that same axis. Force pairs always act on different objects. So let's just highlight this. So again, same line of action. They act on different bodies. You're not going to see two force pairs on the same object. They are the same type of force. And this is very important. They are equal and opposite in direction. Okay, and they always concern two forces. That's why they're called a pair. So my example here is I drew a free body diagram of a man that's just standing on the surface of the earth. The man would feel a normal force of the earth pushing up on the man. If I was drawing a free body diagram of the earth, then the earth would feel the normal force of the man on the earth. These are called force pairs. They're in equal direction, but they are the same magnitude. Here I have a gravitational force. Okay, the earth has a gravitational force pulling down on the man. At the same time, the man has a gravitational force trying to pull the earth toward the man. Okay? So these here are going to be force pairs. So you have two sets of force pairs. You have the force pairs of the normal force, and you have the force pairs of the gravitational force. So let's look at this. I have a man standing on a box, and the box is on the earth. So if I was looking at my force pairs, again, here now I'd have the normal force of the box on the man because the man is standing on the box. I would still have the gravitational force of the earth on the man. Okay? I'm not including the gravitational force of the box and the man on each other. Okay, you could do that. It would be extremely small values, so here I do not put those in. So again, the man would feel the normal force of the box on the man, the gravitational force of the earth on the man. When I draw the force pair over here, I'd have the normal force of the man on the box. Again, same magnitude, opposite direction. When I draw the free body diagram of the box, it would feel, again, like I said, the normal force of the man on the box. It would also feel the gravitational force of the earth on the box, and it would feel the normal force of the earth pushing back up onto the box. So it would have three forces applied to that, while a man would have two forces. If I drew the free body diagram of the earth itself, it would feel two gravitational forces. It would feel the gravitational force of the man on the earth. Again, this one and this one would be force pairs. It would also feel the gravitational force of the box on the earth. This one and this one would be force pairs. And it would also feel the normal force of the box on the earth, and these two would be force pairs. So let's look at a picture here. I'm going to draw these. Here I have a 28.5 kilogram box M1 on the table and a 13.5 kilogram box M2 placed on top of the 28.5 as shown. We're going to draw a free body diagram of each box as well as the table. Now I'm not going to include any of the numerical values of the force. So what I would do here, let's go up to a pen, let's start with the M2. M2, I would draw myself a little dot. I would draw two forces here. Like this, okay? Again, these are going to be the same magnitude, so I'll put a slash through it and a slash through it. I will label this one as the force, and that would be a gravitational force, and that would be the Earth onto M2. And you notice I'm using a slash instead of an arrow. Again, you feel free to use the arrow. Again, I'm drawing a free body diagram of the M2. Okay, this would be my normal force. And this would be M1 pushing up onto M2. Alright, so that's the free body diagram of M2. That's all M2 is going to feel. M2 is not going to feel any type of force from the table pushing up onto M2 unless we include gravitational force, and we do not include the gravitational force typically of a table onto M2. Yes, it does exist, but it's an extremely small value. Alright, so now let's jump to M1 and draw the free body diagram of M1. To draw M1, again, I draw the dot, and let me go ahead and label this so if you come back to it, this is the force diagram of M2 over here. Okay, so for M1, it feels the M2 pushing down on it. So I'll label that as a normal force. And this is M2 onto M1. M1 also feels a gravitational force. Force of gravity. And this is the Earth onto M1 here. Okay, everything is going to be balanced, so this is going to feel a force going up. And this would be a normal force. And this would be the table onto M1. Now notice here, on this free body diagram is the M1, M1 always comes last. And that's because I'm drawing the free body diagram of the M1. Same way over here, I had M2 here, M2 here. It always comes last. So that's what the free body diagram would look like of M1, M2. Now let's try to draw the free body diagram of M1. I'm sorry, of the table. I think I can get it right here. Let's try it here. So if I was drawing the free body diagram of the table here, we'll do the gravitational force first. So there'll be some force of gravity of the Earth onto the table. It would also feel M1 coming down. So it'll be a normal force of M1 onto table. And this would feel a normal force. Put this better into play. So there's my force normal. And again, this would be Earth onto table. Same way as before, notice the table comes last. Okay, so that would be the free body diagram, and we will typically not draw the free body diagram of the Earth. So that's the free body diagrams of M2, M1, and the table. Let's look at some other examples here. Here I want to draw a free body diagram of a bird flying horizontally. We'll say it's flying at a constant velocity where wind drag is present. Again, we immediately start with a dot to represent the bird. We'll have the force of gravity coming down. I'm going to draw the arrows all this time, and then let's So this would be the force of gravity. This is going to be the earth onto the bird. This is going to be some type of lift force. So I'll call this a lift force. And what's causing that is the air onto the bird, pushing up on the wings. So say A onto B. Put an arrow here. We'll make these, what slashes mean they're congruent, same magnitude, opposite direction. Here, there's some drag force. So if I go at constant velocity, there has to be some type of force here. So I'm going to call that some type of pushing force. And again, that's the air pushing onto the bird. Because remember, the bird can't cause a force on itself. This will be some type of drag force. And with drag forces, you can put a D if you'd like, or sometimes they put FD, meaning it's a frictional drag force. But I'll put D, and what's causing that, again, that's air onto the bird. Okay, if it's going to constant velocity, I put a slash here, meaning they are the same magnitude. Free body diagram of an egg falling from a nest in the tree will include air resistance, and this time we will assume the egg is accelerating downward. It would only have two forces. This would be the force of gravity. This would be earth onto the egg. If you have two E's like earth and egg, I would go ahead and spell one out. This would be my drag force, air resistance. So again, you could put D, or you can put some type of frictional force. I will go put D, and that would be the air onto the egg. Again, if it's accelerating, this force here would be shown longer than this force here. We would not draw any arrows. If it was moving at a constant velocity, then we would show these being the same length, and we would put slashes, meaning that they have the same magnitude. Okay, baseball. This being thrown by pitcher that's left the pitcher's hand. Okay, we're going to let the ball be moving to the right. If it's moving to the right, the only thing it's going to feel are two forces. It's going to feel the force of gravity, the earth onto the ball, and it's going to feel some type of drag force, the air onto the ball. And that's all it's going to feel. Even though it's moving to the right, it's not feeling a force that's going to the right. That ball, once it leaves that pitcher's hand, is slowing down because of the drag force. The ball is also starting to accelerate downward because of this force here. Those are the only two forces it's going to feel. Okay, if the pitcher was throwing some type of curved ball and it has a lift, causing the ball to have a lift, then you could put a small force showing a small force going up, having some small lift force. Okay, let's do one more here. We got to draw a free body diagram of a blue object that moves at a constant velocity across the table. The book does not move. Draw a free body diagram of the book. So we're going to do the blue object and the book. So the blue object, immediately we draw the force of gravity coming down here. I'd have a force going up to here. So this would be the force of gravity. And that's going to be the earth onto the blue object. This would be my normal force. And that's going to be the book onto the blue object. Okay, I have a pushing force here. Again, you don't know what's causing that, so I'll put a force, I'll put a push. It may be a hand's pushing it. Let's say a hand, I'll do something like that. And then you could just say push hand onto blue or something like that. If it's moving at constant velocity, then I also have to have a force going back here. I'd put a slash immediately through this if it's moving at constant velocity, because I have to have balanced forces. And I would call that as some type of friction, and it would be a kinetic friction if it's sliding. So put friction, kinetic, and again that's going to be the book onto the blue. And that's a free body diagram of the blue object itself. And if I was drawing the book, free body diagram of the book, I'd have the force of gravity of the earth onto the book. I'd add the force of the blue onto the book. Oops, not quite straight. This would be the force normal, and I'd call that the blue onto the book. I'd have a force going up here. This would be force normal of the table onto the book. We used to back up. We didn't use we just used B for book, didn't we? Okay, again, be careful with since you got a blue and a book. Make sure you label them both, and again, there's nothing says you can't call that book if you choose to. But if you're going to call it book, then call it book up here also. All right, it has a pushing force. So it's not, if it's going to feel, it's going to feel a force going back the other direction from the blue. Oops, sorry, let me go back this way. It's going to feel one going this way. Run out of space here. But this force, I'll label it over here, is going to be the force of friction, and it's going to be kinetic, and it's going to be blue onto book. Okay, and I'm going to color these. These two are force pairs. So I can grab that. Maybe even grab those. I'd like to grab them both. Those are force pairs, okay? Equal magnitude, opposite direction. And if that book is not moving, then that book must also be feeling a friction. And this one would actually be static friction. Again, if you don't quite understand what I'm talking about these, will be other videos on defining the difference between kinetic friction and kinetic and static friction. Okay, so I have frictional force. This would be a static friction, and that would be caused by the table onto the book. Right, so that would be my free body diagram, and again, you could put a slice through here, meaning they have the same magnitude, opposite directions, because they're balanced and the book is not sliding. Alright, so this completes the video on free body diagrams. I hope this helps you understand how to properly label them, and also the importance of it, because now if I tried to solve this from a physics standpoint, it's much easier when I start summing up the forces in the horizontal and vertical directions. All right, best of luck.